Okay, once you finish the previous recording, the one that I sent first, people, this one, the name of this recording is Confidence Intervals Continue. So it's just building on the previous stuff that we've already done and the previous recording. So once you finish that one, you can go to this one. I will introduce you to some more apps and bootstrapping and concepts. Okay, enjoy it. People, my objective is simply to explain confidence intervals, to make sure that you can discuss it and know exactly what it is. We're going to do heaps of revision, and then I'm going to introduce you to some apps. And the last concept that we will do for today is bootstrapping, but that's really easy. What about confidence intervals for a proportion? The examples we've looked at so far have related to measurement data and means. We may also wish to find confidence intervals for other statistics and other types of data. It's very common to see confidence intervals for proportions, which come from nominal data. There's a rule of thumb for political polls. For most political polls in New Zealand, the sample size is around 1,000, and that leads to a margin of error of plus minus 3.1%. The margin of error is the amount we add to or subtract from the stated percentage or proportion. So if a news article states that the approval rating for a particular leader is 45%, then we can add and subtract 3.1% to find the range that we are 95% confident includes the population standard deviation. When a percentage moves 1 or 2% from a previously reported percentage, it can be pointed out that this is within the margin of error. That means the two sample percentages that are less than 3% apart could result from exactly the same population. The formula for confidence intervals for proportions. In the formula here, P is the stated proportion from the sample. You know what a proportion is. Say, for example, 10 out of 100 or 50 out of 1,000 or 550 out of 1,000, whatever it is. But that's a proportion. So the Z value is taken from a standard normal distribution and generally takes one of the values shown in the table, depending on the level of confidence you wish to have. In other words, we simply read the Z value from a table, and there's a formula that we use to determine our confidence levels, and the confidence interval is often called the margin of error. Okay, people, we're now slowly but surely going to look at the effect of changing the confidence level, and later on we will also look at the effect of changing the sample size. And I want you to use this online calculator, EpiTools calculator, and there's the link that I've given you, and remember to take this link as well as all the other links that I've given you so far. So save this link with the previous one. Every time I say it to you, and later on if you're going to look for links and you have to go back to all your notes, it will be very difficult. So just stay up to date. So in the EpiTools calculator, the default distribution is that of a Wilson distribution, but just remember to change it to a normal Walt distribution. So the way that we're going to use the EpiTool calculator, enter a sample size of 1,000. Number 2, enter the number positive as 510, and this is from 1,000 multiplied by 0.51. Note that it asks for a count here, not a proportion or a percentage. So a count. Enter the confidence level at 0.95 for the 95% confidence interval and number of decimal places at 4. Number 4, scroll down to 2, normal approximation, and submit it. So this gives the limits of 0.4790 and 0.5410, which you can then convert to percentages. Beware, it takes a time for the apps to do it. So just be patient. So people, there was your inputs, what you were supposed to put into the app, and then the results. You will get the lower confidence level as 0.4790 and the upper one as 0.5410. And yeah, just make sure that yours looks like this. And now I want to ask you to use this app and please complete the table. In other words, you will see there's empty values, 4 empty values. So you will find your answers on the next slide, but now first pause and do it before you look at the next page. Okay, here is your completed table. At the bottom, you will see what the apps would have spit out, the answers, and then you would have taken those answers, look at my arrows, and just simply put them in the table to complete it. What happens? What happens to the margin of error and the width of the confidence interval as the level of confidences increases? In other words, look at the confidence levels. When they increased, what happened to the margin of error? You know it by now, but as the level of confidence increases, the margin of error increases and the width of the confidence interval increases. We need a wider confidence interval to be surer that our interval includes the population proportion. People, now we're going to use the UCSF tool calculator. And note, if you use the UCSF Clinical and Translational Science Institute calculator, your answer will be found under 2. Normal approximation to the binomial calculation. In other words, you won't find it at 1, you will find it under 2. So the UCSF tool calculator, there's the link that I've given you. So you can just go to your PDF slides and press Ctrl Enter and it will take you to this tool. So go to the UCSF tool calculator and enter sample size 1000. And then enter number positive as 510. This is from 1000 times 0.51. And note that it asks for a count here, not a proportion or a percentage. In other words, people, it's doing exactly the same thing that we already did with the previous app. So you can, at the end of the day, decide which one you want to use, which one you prefer. Enter a confidence level at 0.95 for the 95% confidence interval, and then calculate it. Press calculate. And then scroll down to 2, your normal approximation to the binomial calculation, and submit. People, this is what you would have found. In other words, you would have found something like here on top, the sample size and the number in the sample with the result of finding in question 510 and then a 95% confidence interval. And that would have given you your confidence interval that would have been 0.4790. So we're just going to multiply it with 100 to get like a percentage, and that will be the lower bound, and the upper bound will be 54.10. So we can put it in our table. And now please pause the recording and do it for the rest of the values, the missing values, and complete the table, please, by using this app. People, so this is how your completed table will look like. And where did you get the values from? Just look at the bottom. And if you still don't understand it, please pop me an email and I'm very willing to help you. But I'm sure you will be able to understand it on your own. If you don't, listen to the previous recording again and listen to this one again and make sure that you can do it. What we have done so far is simply to look at the effect of different confidence intervals. But now I want you to explore the effect of sample size. So please complete this table and do it by using the online calculator, any one of the two. And I want to ask you something with a big smile. Does this one look familiar by now? The 47.9 and the 54.1, because we've already done it in the previous calculations. Okay, people, I hope you've seen it, but over here on the left-hand side, if you look at that orange arrow, you can see the different sample sizes, 500,000, 4,000, and 10,000. So as the sample size increases, the margin of error decreases. In other words, if we take a bigger sample, we're getting nearer to the size of the population. In other words, then we can be more sure that our sample mean will be the same as the population mean. It will give us a clearer indication. So if the margin of error decreases, the width of the confidence interval will also decrease, because the margin of error is basically half of the confidence interval. So what happens? What happens to the margin of error when we increase the sample size by a factor of 4? In other words, we increase the sample size from 1,000 to 4,000. Interesting, people, as the sample size increased by a factor of 4, the margin of error decreases by half. Okay, people, now we've basically looked at the effect of different sample sizes, and we've already looked at different confidence intervals, but now we're going to keep the confidence intervals and the sample sizes the same, and we're going to look at the effect of the sample proportion. In other words, a proportion, I've told you a proportion will always be something like 600 out of 1,000 or 510 out of 1,000. So exploring the effect of the sample proportion, what will happen? Take a look at the information in this table, and please, people, I've given you a hint there in yellow. If you want to determine the margin of error, you're going to use the upper bound minus the lower bound, and you're going to divide it by 2, and then you will get your margin of error. So now that you know it, please, people, you can do it. Use your app and please complete the table. Okay, people, your completed table should have looked like this. But now I want to ask you a question. What happens to the margin of error and the width of the confidence interval as the sample proportion gets further away from 0.5? In other words, if we move up or down away from 50%, what will happen to the margin of error? People, as the sample proportion gets further away from 0.5, the confidence level decreases. Can you see it? And the margin of error becomes smaller. Now I want to talk about confidence intervals for the difference of two means. In other words, if two means are different. They're not the same. Often in statistics, we're comparing two groups to see if there is a difference between the means. Means, middle values. We can compute the difference between the two means using subtraction. And this gives us a point estimate or a single value for what the difference is between the samples. That's kind of like logic up to so far. If the means of two populations are the same, then the difference between them will be 0. Usually, we will be examining our confidence interval to see if 0 is a possible value for the difference between the two means. If 0 falls in the confidence interval, we can accept that the two population means could be the same, even though the sample means differed. People, every now and then we will jump back and do a little bit of revision of old stuff. And this graph that you see over here shows the household income for people with the bottom one and without partners, the top one, the two different box plots that I'm talking about and the dot plots. So what can you say about the household income for people with partners compared to the people without partners? So please, people, report fully on this and then compare your effort to the effort that will follow on the rest of the PowerPoint slides. Okay, people, if you start with the obvious, let's start with central tendency. The median for the people with partners is well to the right of the median for people without partners. Even the lower quartile for the people with partners is greater than the upper quartile for people without partners. Make sure that you understand everything that I've said so far. And it's clear that the household income for people with partners tends to be greater than the household income for people without a partner. Remember that secret phrase, tends to, because we can never say that it's definitely going to be like that. Okay, because some of the range, there will be overlap. So it is clear that the household income for people with partners tends to be greater than the household income for people without a partner. This makes sense, as these are potentially two incomes in a house when a person has a partner. In other words, if you've got a partner, there's two incomes compared to a single income for a person without a partner. When we talk about the spread, we can also see that the spread of incomes for people with and without partners, it's about the same. The interquartile range for both is kind of similar. In both groups, there are some high values which are a long way from the rest of the data. And this would reflect a small number of people in each group who have considerable higher incomes. And then when we look at the shape of the two distributions is quite different. In the group with no partners, a considerable number have 0 or close to 0 income, which tails down as the income increases. The group with partners has a more bimodal distribution with two peaks at around 40,000 and 60,000. Okay, just look at it, study it a bit, and make sure that you agree. And then you can continue. Exploring the data. You can now explore the data in more detail using Insight Lite. Use the Household Savings Survey of 2003 data set and load it into Insight Lite. And then you choose the income variable as the first variable and the partner variable as the second variable. I've put yellow here on the slide behind it because That's actually what it was supposed to be, but it's not part of the name given in the Excel sheet. So just use income and partner. So then click on the inference tab, because we can use Insight Lite to find confidence interval for the mean household income in each of the groups. And you should see a graph like this one. In other words, if you look at the bottom of this slide, this is basically what you should see on your screen if you've done it correctly. Now I have a question for you, and this is simply, what else can you find out about the data, and what would you say about it? I want you to give the group means with a 95% confidence intervals and write down what the two confidence intervals will tell you. Please do it, pause, do it, and then after you've done it, you can resume the recording and see if you are correct. So people, just by going to inference, we will find the following, and we are now going to focus on this screen that I've taken a screenshot for you, and we are now going to focus on that data. But that's basically what I wanted you to, or where I wanted you to go. So if you're not there yet, please go there and get the confidence intervals and do what I've told you. Tell us what it's telling you. Okay, people, here, I've cut out that small portion out of the previous screenshot that I've shown you. And this is our confidence intervals that we got. A group means with 95% confidence intervals. And there you can see it if you do not have a partner. If you're all on your own, your salary was probably or your household income was probably in the region of 20,519, and with a partner 56,539. So we are 95% confident. If we now interpret this data in front of us, we are 95% confident that the mean annual household income for people with partners lies between 52,000 and 61,000. Because I'm now looking at the lower and the upper levels. And we are 95% confident that the mean annual household income for people without partners lies between 17,300 and 23,700. Can you see I've again just rounded the numbers? We can see that these two intervals do not overlap at all. So the difference between the mean sample values is 56,539 minus 20,519. People, this is basically the most important thing that you have to focus on, and that will give us 36,020. So on average, the group with partners has an annual income that is 36,020 higher than the group without partners. And the reason why we can be so confident, because there was no overlap. And how would you report this? It's interesting that the average for the group with the partners is more than twice the average of the group without partners. This would suggest that it's not just having two incomes that increases the household income for people with partners. Okay, so in other words, what we are seeing, it's not only because they've got like a double income. It's probably also due to the fact that they could use some of those surplus funds and invest it, and maybe get an investment income or buy an extra property, whatever it is. So the difference between the means of the two groups is 36,020. People, that one in yellow, that's basically easy to understand, and you can easily use a calculator to determine it. We used to be able to give a confidence interval for this, and that's what the computer is going to do. and that will be lower of 41,814 and upper 30,226. So see if you can write out how you would interpret and report this. Okay, people, it's always good. You will see I'm doing it, but it's always good to round the values. So the 95% confidence interval for the difference between the two means is 30,200 and 41,800. So that's our confidence interval. You know how we write it down. We are 95% confident that the mean household income for people with partners is between 30,200 and 41,800 more than the mean household income for people without partners. In other words, people, we can't say it will be exactly 36,020. I've already explained this a lot to you. You only have like a certain confidence that it will fall within that specific range. A 95% confidence. And even then you can't be 100% sure because there's a 5% probability that it will even fall outside that range. So note, expressing confidence intervals correctly and precisely is very difficult. And maybe you feel clumsy or you feel, I can't do this. But remember, the more we do it, the better we get at it. And so don't be discouraged. It's a little bit, it takes a little bit of practice of doing, just like accounting. The more you do it, the better you become at it. Now use the dessert data set and load it into Insight Lite and choose the paper person variable as the first variable and the gender variable as the second variable. And then get the confidence intervals and discuss it. People, this one is a difficult one, tricky, but try and do it. Okay, people, if you look there at estimate, you can immediately see that in the sample, the mean amount men said they paid per person for takeaways was greater than the mean amount women said they paid per person for takeaways. The confidence interval is $3.15 and 0.29, okay? Men could pay between $3.15 more and 0.29 less than women. Why do I say less? Because remember, if you look at the confidence intervals, you will see it was a minus $3.15. And if you look at what the computer did, because we've put it around male versus female, so it was taking the females, which basically have the smaller numbers, minus what the males estimated, which was basically the bigger numbers. So that's why we got negative numbers. But if we think about it, we will see, okay, men are actually paying the $3.15 more, and yeah, there's a probability that they can even pay 29 cents less than women. So what you see here, and this is what made it really tricky, the value of 0 discussed earlier falls within the confidence interval. So if you look at the bottom range, you will see the lower confidence interval, the lower range is minus 3.15 and the upper is 0.29 or 0.2888, whatever. So the value of 0 discussed earlier falls within this confidence interval. Okay, people, can you see that? Showing that there may be no difference in the population means. That's what we discussed way earlier as well. But now this is very practical because remember, I've told you if you look at the differences between two means and you see that it's 0, then there's a possibility that, yeah, there's no difference between the two means. Since it seems it could go either way, we can't see that there's any difference in what the men and the women say they pay for takeaways per persons. In other words, people, it's going either way in the sense that, yeah, even though it kind of like looks as if men pay more, it can be that men are in reality actually paying 29 cents less. So, in terms of Helen's desserts, this could mean that there's nothing to indicate they should treat men and women differently with respect to marketing. People, this is what's making stats a little bit difficult, but once you've got the reasoning behind it, it will be easy for you. Just hang in there. People, we use a sample proportion to calculate the confidence interval on either side of that sample proportion. If we do it many times, we will have a different sample proportion every time, a different center every time, and the margin of error might change because we are using the sample proportion to calculate. Can you see that? So the first assumption that has to be true before making any claims about the confidence interval with confidence is that our sample must be random. If you're trying to estimate the proportion of people that are going to vote for a certain candidate, but you are only surveying people at the senior community, well, that would not be a truly random sample. And the same is true if we were only to survey people at the college campus. People, it's not representing the whole population. So you can see that at the end of the day, our conclusions will be wrong. It will be skewed. Like with all things with statistics, you really want to make sure that you're dealing with a random sample and take great care to do that. The second thing that we must assume, and this is sometimes known as the normal condition. Remember, the whole basis behind confidence intervals is that we assume that the distribution of the sample proportions, the sampling distribution of the sample proportions, has roughly a normal shape. But to make that assumption that it's roughly normal, we have this normal condition. And the rule of thumb here is that you would expect your sample to have more than 10 successes and more than 10 failures each. So you would expect per sample more than 10 successes and 10 failures each. So, for example, if your sample size was only 10, let's say the true proportion was 50% or 0.5, then you wouldn't meet that normal condition because you would expect 5 successes and 5 failures for each sample. Now, because usually when we're doing confidence intervals, we don't even know the true population parameter. What we would actually just do is look at our sample and just count how many successes and how many failures we have. If we have less than 10 on either one of those, then we are going to have a problem. So you want to have at least greater than or equal to 10 successes or failures on each. If you do not see that, then the normal condition is not met, and the statements you make about your confidence interval aren't necessarily going to be as valid. Long and short of the story, people, you should look at this in order to make sure that you work with a normal distribution. I'll come back to this, don't worry. So extremely important whenever you're doing research, even in statistics, people, random sampling is extremely important. The sample must have been collected using a random process. In other words, where you throw all the numbers in a hat and draw one. You know the random process. In particular, each member of the population must have equal probability of being selected. The moment that that's not true, then it's not random sampling. And then the next thing that we are going to look at is independence, or the next thing that is important. The sample values must be independent of each other. This means that the occurrence of one event has no influence on the next event. Usually, if the items were selected randomly, we can assume that the independence condition is met. So in other words, everything is just coming back to random sampling. Okay? Sample proportion of the population, the samples should be no bigger than 10% of the population. Sample size condition, people, the sample size must be sufficiently large. It's important. In general, a sample size of 30 is considered sufficient. If the underlying population distribution is similar to normal, you can probably manage with a smaller sample. Okay, I've promised to come back to this. Specific to confidence intervals of proportions. When proportions are too close to 0 or 1, the normal-based inference is not valid. Computer programs luckily check for this, but we need to know that n multiplied by p and n multiplied by 1 minus p, in other words, I told you the two together should always be 1, are both greater than 10. In practical terms, this simply means that at least 10 people gave that response, or at least 10 people did not give that response. Exactly, now it will be very clear to you. Other ways of finding confidence intervals, people, in this course, as in many current statistical analysis, we're using normal-based inference. However, this limits the statistics for which we can easily compute confidence intervals. So we will look at something more. So people, this other way that I've been talking about that we can use in order to determine confidence intervals, people, we call it bootstrapping. The term bootstrapping comes from the saying to pull yourself up by your bootstraps. And it simply means to improve one's position by one's own efforts. People, you've already done bootstrapping. We've done it in Insight and you've not even realized it. So it's very, very, very easy. In some circumstances, a bootstrapping approach is used for inference. A bootstrapping approach samples the data in the sample repeatedly in order to recreate the population. You may have noticed that Insight Lite offers the bootstrap as an alternative to normal-based, and that there are more statistics for which the bootstrapping method can calculate confidence intervals. So long and short, you've already seen it. So bootstrapping is based on two concepts. The best information we have about the population is the sample. That's concept number one. The best information we have about the population is the sample. And people, again, I'm using Dr. Nick's work, so I'm giving all the credit to her. People, you know that normally we take a sample from a population. And it works. But over here, resampling from the sample produces a distribution very similar to repeated sampling from the population. This is what we discovered. This is knowledge that we already have as statisticians. Okay? So bootstrapping, resampling from the sample produces a distribution very similar to repeated sampling from the population. As long as you can see that bootstrapping is resampling from the sample. And we do it repeatedly. If we really need to know exactly what the population parameter is, we need to measure the entire population. That's a problem for us people, cost-wise, and it's not practical. But we cannot usually do that. And that is why we take a sample. And every sample we take, unfortunately, is likely to be different. So we need to know how different these samples from one population are likely to be to work out how far off the mark we could be with our estimate of the population parameter. We could take repeated samples of the population and work it out from there. But actually, if we could do that, we might as well take one big sample or measure the population. The point is that we have only the sample data and we wish to get the best possible information we can from it. So we pretend that the sample is the population. It is the best information we have. Then we take a whole lot of samples of the same size from our sample. We need to sample with replacement. In other words, every time you've taken something out, you put it back. Otherwise, each sample will be identical. So these are called resamples or bootstrap samples. This is pretty time-consuming, and the reason why nobody did this much in the past was because it was the age before computers. But nowadays, luckily, we've got computers working for us. So this is good news, and the better news is that you can do it for free on Insight. We took a sample of 15 apples from our orchard. People, this is Insight, like I've said. These are their weights. The mean weight of the sample is 149.27 grams. So there's one sample that we've taken. We then took a bootstrap sample of size 15 from this that looks like this. People, if you pause the recording, see if you can see the difference. I hope you have noted, but some of the values appear more often than they did on the original sample, and some do not appear. Look at the yellow arrows, and look at the blue circles on top. Okay, people, we will take another bootstrap sample that will look like the previous ones, and another one, and we will get the computer to take 1,000 bootstrap samples for us. We are interested in the distribution of these values over the mean, the center, as they give us a very good idea of how our actual samples from the population are distributed. And this is called a bootstrapping distribution. So each gray circle represents the mean from one resample. And now we can use it to determine a bootstrap confidence interval. I told you we use it to determine a bootstrap confidence interval by using the central 95% of the values. And this gives us a result of 147 to 151 grams in this slide that you can see over here. Very, very well presented. It's worth pausing it and just look at Dr. Nick's presentation on this specific slide. So people, it is reasonable to say that the mean weight of the apples in the orchard lies between 147 and 151 grams. People, and even a better way to say it, this is kind of like the way that I prefer, or it is a fairly safe bet that the true value of the mean is one of the values in this confidence interval. If you say it like this, I will love it. Okay, people, this table, the difference between normal-based inference and bootstrapping inference. In normal-based, it's in common use for decades already and in most disciplines. And it can be calculated by hand. And it needs a big enough sample for the central limit theorem. People, it's used for means, but not medians. It may be difficult to understand. It uses summary values of the sample, and it gives the same answer every time. Then if we look at bootstrapping, people, this is really great. It's a great method that we can use thanks to our computers. People, it's becoming more and more common, but it's not yet in frequent use. We need computers because thousands of iterations are needed. People, it works on any size sample. So this is really great. It can be used for means and medians. It's arguably more intuitive. In other words, it's actually easier to understand. It uses all information about the distribution of the sample. It gives varying answers each time. Reporting confidence intervals. Sometimes statistical analysis can seem vague, but in some areas you need to be very precise. And one of these precise areas is interpreting confidence intervals. So what does it mean? We calculated that the 95% confidence interval for the mean number of takeaways per month for all New Zealanders is between 4 and 5.4. Okay, I'm making a statement to you. There it is. You can pause the recording, look at it, write down what you think that means. This sentence here, we calculated that the 95% confidence interval for the mean number of takeaways per month for all New Zealanders is between 4 and 5.4. And people, the reason why this is important to do is to help you identify any misconceptions that you might have about confidence intervals. Okay, people, there's several different statements that we're going to look at that students made in the past, and we're going to look at them. But in the table here, you can see correct or acceptable statements. So one of the students said, if we were to take 100 samples like this one and calculate the confidence intervals in the same way, we would expect about 95 of them to contain the population mean. Another statement, okay, but this is a very correct or rigorous statement. A statistician would be happy with it. That's the critique on the first statement. Let's now look at the second statement. We are 95% confident that the mean number of hours per week for students in the population lies between 3 and 10.1. This is also correct, providing the numbers are correct and not quite as long as the previous statement. Number 3, it is possible that the mean number of hours in the population is less than 3 or greater than 10.1, in example, outside the confidence interval. Critique, this is correct, though it doesn't explain what the confidence interval is. So the best one so far is the first statement, okay? So the last statement, the fourth statement, we are fairly confident that the mean length of time for the population is between 3 and 10.1. This is correct, but a rather information interpretation of a confidence interval. If we say fairly confident, it is usually 95%. Very confident is usually implying 99%. So remember that. Fairly confident is usually 95%. Very confident implies 99%. Over here we've got some incorrect statements. There is a 95% probability that the population mean lies between 3 and 10.1. People, the critique, we should never use the word probability when talking about confidence intervals. People, I sometimes use it myself to explain it to you, but it is wrong. It's better to say we expect. Okay? So we should never use the word probability when talking about confidence intervals. Probability only applies to things in the future. We are 95% confident that the mean number of hours per week for students in the sample lies between 3 and 10.1. People, we know exactly what the mean number of hours per week is for the sample. We've just measured it. Confidence intervals are always about the population parameter. So that's, of course, wrong. 95% of the students spent between 3 hours and 10.1 hours on their course. People, this is also totally incorrect because it's talking about the distribution of the students, whereas a confidence interval is about the distribution of the sample means. In other words, confidence intervals are basically about the distribution of the sample means only. So that's what we're interested in, okay? And that's why it's been wrong. Here's some statements that students made, and it's your job to evaluate the statements. You're a teacher, and you're supposed to mark their work. Kara, I think confidence intervals tells you the interval that most of the data will lie in. Most people eat either 4 or 5 takeaways per month. Sam, I think a confidence interval tells you the range that you are sure that 95% of the population lies in. In other words, 95% of New Zealanders get between 4 and 5.4 takeaways in a month. Fan, it is something to do with the mean. We are 95% sure that the sample mean is between 4 and 5.4. Rachel, but we know the sample mean, so maybe it's about the population mean. Let's evaluate the statements. Kara said, I think a confidence interval tells you the interval that most of the data will lie in. Most people eat either 4 or 5 takeaways per month. People, Kara's statement is not correct. The confidence interval tells you where you think the mean will be, not the data. So it's all about the mean. This answer is not clear about which data she is talking about. Is it the sample or is it the population mean distribution that she's talking about? Sam's statement, I think a confidence interval tells you the range that you are sure that 95% of the population lies in. In other words, 95% of New Zealanders get between 4 and 5.4 takeaways in a month. People, Sam's statement is getting a little bit closer because it explicitly mentions the population, but it confuses the spread of the population with the spread of the sampling distribution of the mean. Okay, people, and in this conversation, Fan and Raquel basically talked about the same thing, so I'm just going to evaluate it in one. Fan, It is something to do with the mean. We are 95% sure that the sample mean is between 4 and 5.4. People, this is getting closer. However, we know that the sample mean is right in the middle of the confidence interval. Since the interval was calculating using the margin of error around the sample mean. Okay, so he's still confused about the sample and the population. Rachel, but we know the sample mean. This is what she answered. So maybe it's about the population mean. And Rachel's statement is correct. It's about the population mean. So just remember that. Whenever we talk about population or confidence intervals, it's about the population mean. I want to do some revision questions just to end the topic, and it's always a good way to end the topic to basically test your learning, what you've learned. So, which is the best statement of the relationship between descriptive statistics and inferential statistics? Inferential statistics is quite different from descriptive statistics as it calculates different summary values. Or, we need to have data from the whole population for descriptive statistics to be meaningful. Sample data can only be analyzed by inferential statistics. Or we use descriptive statistics when we have population data and inferential statistics when we have sample data. Or when we have sample data, we can use descriptive statistics to explore relationships and inferential statistics to see if we have evidence that these effects exist in the population. So just choose the best statement. Pause the recording, do it, and then resume. People, of course, it's the last one, it's the best. When we have sample data, we can use descriptive statistics to explore relationships and inferential statistics to see if we have evidence that these effects exist in the population. Number 2, we plant 300 kauri seedlings and study the growth rate. We use this information to draw conclusions about the growth rate of all kauri seedlings. Which best describes the sample and population in this study? The sample is all the 300 seedlings and the population is all kauri seedlings. The sample is a selection of the 300 seedlings that we measure, and the population is the entire plantation of 300 seedlings. The 300 seedlings are a population, and so is the population of all kauri seedlings. The sample is all kauri seedlings, and the population is the 300 seedlings that we monitor and measure. So choose the correct one and then resume the recording. So people, the sample is all the 300 seedlings and the population is all kauri seedlings. We collect data about workload from a sample of 200 teachers and calculate a 95% confidence interval for the mean number of hours that they worked in the previous week. Which statement about confidence intervals is not correct? The confidence interval will probably contain the mean number of hours teachers in the population worked in the previous week. The confidence interval will definitely contain the mean number of hours the teachers in the sample worked. It is possible that the confidence interval will not contain the mean number of hours teachers in the population worked in the previous week. It is possible that the confidence interval will not contain the mean number of hours teachers in the sample worked in the previous week. Choose the correct one. What I mean with choose the correct one, choose the one that is not correct, but make sure that it's the correct one that you choose, the correct answer at the end of the day. Okay, people, it is possible that the confidence interval will not contain the mean number of hours teachers in the sample worked in the previous week. So, because you had to choose the intervals, that is not correct. I've highlighted it for you in yellow. Which of the following statements about sampling is correct? The best way to avoid sampling error is to take a really large sample. Because the sample is only a selection of objects from the population, it will never be a perfect representation of the population. It is possible to avoid sampling error if you are careful how you take a sample. Usually we can find out about the population by measuring every item in it. It is not often necessary to take a sample. So choose the one which is correct. People, because the sample is only a selection of objects from the population, it will never be a perfect representation of the population. There's one you will probably need a piece of paper and a pencil, calculator, whatever. The following inference information relates to the amount people would pay for a serving of ice cream sundae. Which number is the star replacing? Inference information: lower 5.162, mean 5.52, upper star. Okay, and then we've got 5.878 as a possible answer, or 6.878 as a possible answer, or 5.678 as a possible answer, and 5.52 as a possible answer. Just choose the correct one for the number replacing that star. In other words, the upper limit. Okay, people, that was kind of like not too difficult, because the mean, the mean is in the center. So basically what you could have done, you could have taken the mean minus the lower, and that answer, you just add it to the mean to get the upper. What effect does increasing a sample size have on the width of a confidence interval with everything else staying the same? It has no effect on the width of the confidence interval. Sometimes it makes the confidence interval wider and sometimes it makes it narrower. It makes the confidence interval narrower. It makes the confidence interval wider. People, it's kind of like logic. If you take a bigger sample, if you increase the sample size, you will be more sure, so the confidence interval will become narrower. Number 7, a marketing researcher decides to report 90% confidence interval rather than 95% confidence intervals. What effect does decreasing the confidence level have on the width of the confidence intervals? It makes the confidence interval wider. It makes the confidence interval narrower. It has no effect on the width of the confidence interval. Sometimes it makes a confidence interval wider and sometimes it makes it narrower. Which one is correct? Pause the recording and please decide before you resume. Okay, people, it makes the confidence interval narrower. A researcher looked at the mean number of pairs of shoes men and women own and noticed that there was much more spread in the number of shoes women own. She calculated 95% confidence intervals for the mean number of pairs of shoes for the two groups. The sample groups of men and women were the same size. Which statement is correct about the relative widths of the two confidence intervals? The confidence interval for the mean number of pairs of shoes women own will be the same width as the confidence interval for the mean number of shoes men own. Number 2, the confidence interval for the mean number of pairs of shoes women own will be wider than the confidence interval for the mean number of pairs of shoes men own. Third option, we cannot draw any conclusion about the relative width of the confidence intervals for the information given here. Last option, the confidence interval for the mean number of pairs of shoes men own will be wider than the confidence interval for the mean number of pairs of shoes women own. People, pause the recording, think about it, do it, and only then continue with the recording. Of course, it will be the second one, highlighted in yellow. The confidence interval for the mean number of pairs of shoes women own will be wider than the confidence interval for the mean number of pairs of shoes men own. Question number 9. You will play teacher again and you will mark students' work. Which of the following is a correct way to state the confidence interval of a mean for the number of hours students spend studying per week? 95% of the students spend between 3 hours and 10.1 hours per week studying. We are 95% confident that the mean number of hours per week for students in the sample lies between 3 and 10.1. We are 95% confident that the mean number of hours per week for students in the population lies between 3 and 10.1. There is a 95% probability that the population mean lies between 3 and 10.1. Pause the recording, find the correct statement. The correct one, we are 95% confident that the mean number of hours per week for students in the population lies between 3 and 10.1. We take a sample of 70 primary schools from throughout New Zealand at random, and we find out whether they have any teaching staff vacancies at present. So which of the following is a statement we can make when estimating a confidence interval for the proportion of schools that have teaching staff vacancies? Every primary school in New Zealand had an equal opportunity of being selected in the sample. All the schools are independent of each other, so they all have a different number of teaching staff vacancies. The distribution of number of vacancies is well modeled by a normal distribution. We have asked more than 50% of primary schools in New Zealand. Okay, people, the correct emphasis was the following. Which of the following is a statement we can make when estimating a confidence interval for the proportion of schools that have teaching staff vacancies? And it's based on a sample because we took a sample of 70 primary schools. People, every primary school in New Zealand had an equal opportunity of being selected in the sample because we rely on random sampling. Simi wants to buy a used Toyota Corolla and collects data on 35 cars on TradeMe. The following information is from an analysis of the number of 4-door and 5-door Toyota Corollas in the sample. Which of the following statements is not correct according to the output? Here is our inference of the distribution of factors, doors, and the estimated proportion with a 95% confidence interval. More than 26% of the cars in the sample were 5-door Corollas. That's the first statement. Second statement, 85.7% of the cars in the sample were 4-door Corollas. Next one, we can be 95% confident that between 3% and 26% of the Toyota Corollas in the population are 5-door. We can be, last one, 95% confident that between 74% and 97% of Toyota Corollas in the population are 4-door. So just choose the one that is definitely not correct. Okay, people, yellow, you can't say that more than 6% of the cars in the sample were 5-door Corollas because remember we've got both 4 doors and 5 doors over there, and it was kind of like easier to look at the rest of the statements and they were all correct, so it was basically only this one falling out. Which of the following statements about confidence intervals is not correct? The confidence interval always contains the population parameter. The more confidence intervals we calculate, the more likely it is that one or more of them does not include the population parameter. With a 95% confidence interval, there is a small possibility that it does not include the population parameter. The wider we make a confidence interval, the more confident we can be that it includes the population parameter. Okay, people, just choose the one that is not correct. People, this should have been really, very obvious. The confidence interval cannot always contain the population parameter. Okay, so that was kind of like an easy one. And let's continue to the next one. When should confidence intervals be reported? Question number 13. Confidence intervals should only be reported for sample data. Confidence intervals should only be reported when we are confident that they include the population parameter. Confidence intervals should be reported for any data that has been analyzed, sample, or population. Confidence intervals should only be reported for population data. Okay, people, confidence intervals should be reported for any data that has been analyzed, sample or population. Which of the following statements about sampling is false? We are best to use the population standard deviation when creating confidence intervals because it is most accurate. To find out about a population, ideally, we would measure every item in a population, but this is often impossible. The sampling distribution of the mean will always have a smaller spread than the sample. Because the sample is only a selection of objects from the population, it will never be a perfect representation of the population. So just find the statements about sampling. Which of the following statements about sampling is false? Find that statement and pause the recording and first do it and then resume. People, we are not going to use the population standard deviation because if we want to measure the whole population, we will get the correct data. So 14A, the yellow one, we are best to use the population standard deviation. That's false, but the rest are all true and correct. So you can have a look at them again. You are looking at an analysis of the amount of time people spent working on an online course and the amount of time the same people spent on Facebook. The 95% confidence interval for the mean number of hours per week they spent on the online course is narrower than the 95% confidence interval for the mean number of hours per week they spent on Facebook. What of the following conclusions is not correct? The relative widths of the confidence intervals are different because generally people spend more time on Facebook than on the online course. There is more variety in the number of hours per week people spent on Facebook than in the number of hours per week they spent doing the online course. We can be more accurate in our estimate of the mean number of hours per week people spend doing the online course than we can in our estimate of the mean number of hours per week people spent on Facebook. The relative widths of the confidence intervals are different because the time spent on Facebook was less consistent between people than the time spent on the online course. People, it's not correct to say that the relative widths of the confidence intervals are different because generally people spend more time on Facebook than on the online course. It's not correct. Which of the following is an incorrect way to state the confidence interval of a mean for the number of hours students spent studying per week? In other words, the incorrect way. We are fairly confident that the mean length of time spent studying per week for the population is between 3 and 10.1 hours. We are 95% confident that the mean number of hours spent studying per week for students in the sample lies between 3 and 10.1. If we were to take 100 samples like this one and calculate the confidence intervals in the same way, we would expect about 95 of them to contain the population mean. We are 95% confident that the mean number of hours spent studying per week for students in the population lies between 3 and 10.1. So you have to choose one that is incorrect. Okay, people, we've done it very thoroughly. And again, I've put the emphasis, I've put the sample in bright, bold, big letters. So we are 95% confident that the mean number of hours spent studying per week for students, people, it can't be the sample, lies between 3 and 10.1. Okay, it's supposed to be the population because we're working with the population. We take a sample of 50 rest homes from throughout New Zealand at random and find out what their broadband speed is. Which of the following is not an assumption that we can make when estimating a confidence interval for the mean broadband speed in rest homes? The distribution of the broadband speed is well modeled by a normal distribution. Every rest home in New Zealand had an equal opportunity of being selected in the sample. The reported speed is a correct assessment of the actual speed. There are more than 500 rest homes in New Zealand. Okay, so which of the following is not an assumption that we can make when estimating a confidence interval? People, you can never say that the reported speed is a correct assessment of the actual speed because people are guessing it. If you've got a survey and then they're just guessing it, okay? So you can never make that assumption. So the one in yellow is wrong, the second last one. Which is the best explanation of inferential statistics? Inferential statistics is a necessary procedure for all data collections so we can know about the population from which the sample is drawn. Statistical inference is the process of drawing conclusions about population parameters based on a sample taken from the population. Statistical inference is the process of drawing conclusions about sample summary statistics based on a sample. Statistical inference is about explaining the relationships between the variables in the sample and variables in the population. So what is the best explanation of inferential statistics? Okay, people, that was something that you had to learn. So, and yeah, there is some truth in all the statements, but the best explanation of inferential statistics is statistical inference is a process of drawing conclusions about population parameters based on a sample taken from the population. Number 19. The following inference information relates to the amount people will pay for a serving of apple crumble. Which of the following statements is correct according to the information? Inference information, mean with a 95% confidence interval. If we look at the lower limit, it's 6.125. The mean is 6.553. The upper limit is 6.981. So none of the people in the sample said they would pay more than $7 for a serving of apple crumble. Second statement, 95% of people in the sample said they would pay between $6.13 and $6.99 for a serving of apple crumble. Third statement, the mean amount that people in the sample would pay for a serving of apple crumble is $6.55. 95% of people in the population said they would pay between $6.13 and $6.99 for a serving of apple crumble. So which of the following statements is correct according to the information? Okay, people, this was an extremely easy one because it was actually given to you. The mean amount that people in the sample would pay for a serving of apple crumble is $6.55. Really easy. Okay, people, Simi wants to buy a used Toyota Corolla and collects data on 35 cars on TradeMe. The following information is from analysis of the number of automatic and manual Toyota Corollas in the sample. Which of the following statements is correct according to the information? People, there's our inference of the distribution of transmission. The estimated proportion with a 95% confidence interval. There we can see it. For automatic gearboxes, lower limit 0.6323, the estimate 0.771, upper limit 0.911. And for manual gearboxes, the lower limit 0.0895, estimate 0.229, and upper 0.368. So we can be 95% confident that between 23% and 77% of Toyota Corollas in the populations are automatic. We can be 95% confident that between 63% and 91% of the Toyota Corollas were included in the sample. We can be 95% confident that between 63% and 91% of the Toyota Corollas in the population are automatic. We can be 95% confident that between 63% and 91% of the cars in the sample are automatic. Okay, so which of the following statements is correct? Pause the recording. Do it and then continue. We can be 95% confident that between 63% and 91% of Toyota Corollas in the population are automatic. Which of the following statements about confidence intervals is correct? The bigger the sample we take, the better chance there is that our 95% confidence interval will contain the population parameter. If we use a poor sampling method, such as a convenience sample, it increases the sampling error. So we need to make our confidence interval bigger to compensate. If we use a good sampling method, we reduce the sampling error, which in turn increases the width of the confidence interval. We cannot know from our sample data whether our confidence interval contains the population parameter we are estimating. So which of the following statements about confidence intervals is correct? People, the last one is correct because we cannot know from our sample data whether our confidence interval contains the population parameter we are estimating. We can never be 100% sure. So if you looked at some of the other things, if we use a poor sampling method such as convenience sampling, it increases says the sampling error? No, it's increasing the non-sampling error. By now, you're supposed to know this, really. Question 22, we collect data about all employees in one region of a retail chain. We use that information to inform the decisions for the whole retail chain. Which best describes the sample and population in this study? The sample is the employees in the whole retail chain, and the population is the employees in the region from which the data is taken. Or the sample is the whole retail chain and the population is the region from which the data is taken. Or the population is the employees in the whole retail chain and the sample is the employees in the region from which the data is taken. Or, last one, the population is each of the stores in a retail chain and the sample is all of the stores in the region from which the data is taken. Pause, answer it, then look at your answer. People, it will be the second last one. The population is the employees in the whole retail chain and the sample is the employees in the region from which the data is taken. Number 23, we collect data about workload from a sample of 200 teachers and calculate a 95% confidence interval for the mean number of hours that they worked in the previous week. Which statement about confidence intervals is not correct? It is possible that the confidence interval will not contain the mean number of hours teachers in the population worked in the previous week. The confidence interval will probably contain the mean number of hours teachers in the population worked in the previous week. It is possible that the confidence interval will not contain the mean number of hours teachers in the sample worked in the previous week. The confidence interval will definitely contain the mean number of hours the teachers in the sample worked. So which statement about confidence intervals is not correct? In other words, once you've made up your choice, remember to look at the other remaining ones because they will all be correct. People, you can't say the confidence interval will definitely contain the mean number of hours that the teachers in the sample worked. Because if you're that sure, why do you need the confidence interval? A researcher decides to report 99% confidence intervals rather than 95% confidence intervals. What effect does increasing the confidence level have on the width of the confidence intervals? It has no effect on the width of the confidence interval. Sometimes it makes the confidence interval wider and sometimes it makes it narrower. It makes the confidence interval narrower. It makes the confidence interval wider. You've already done this one and there's quite a few that's basically just repetition, but please do it. Okay, people, it will make the confidence interval wider. The previous time I've just asked it the other way around, but as long as you know how it works. Which of the following statements about confidence intervals is correct? If we use a poor sampling method, such as convenience sample, it increases the sampling error. So we need to make our confidence interval bigger to compensate. The bigger the sample we take, the better chance there is that our 95% confidence interval will contain the population parameter. We cannot know from our sample data whether our confidence interval contains the population parameter we are estimating. If we use a good sampling method, we reduce the sampling error, which in turn increases the width of the confidence interval. So which of the following statements about confidence interval is correct? Okay, this one was a little bit more difficult, I think, but this was our last question. We cannot know from our sample data whether our confidence interval contains the population parameter we are estimating. I honestly just want to thank you for listening to this whole slideshow and being so diligent, but now it's the end of this slideshow.